Our problem gives us that we have a parabolic drag polar, and that the drag at zero lift and the span efficiency do not depend on CL. And then we're asked to find the maximum lift to drag and the CL and the induced drag at this condition. So to do this, we're going to first determine what CL over CD is by substituting in the parabolic drag relationship. Okay, and then what we would do is look to maximize CL over CD. So to do that, we would take the derivative of CL over CD with respect to CL and set that equal to 0. Okay, so the other thing we'd have to do is to just check after we had found the CL at which that occurred and then found CL over CD. We'd need to check to make sure that it is a maximum by looking at the second derivative of CL over CD. Now, if we look at this function here, what we can see is the derivative here it's not bad, but it's a little complicated. So what we could do instead is to take CD over CL and minimize it, as opposed to CL over CD and maximize it. So another option we have then is find CD over CL, which we just flip around this result over here, and that becomes this expression, CD 0 over CL plus CL over pi aspect ratio, pi e aspect ratio. And then we would differentiate that with respect to CL, setting it to 0. And now we're going to be looking to see then that CD over CL is a minimum in this case. Okay, so we're going to take that approach. They're both equivalent. The math here will be a little easier if we go with this approach here. Okay, so now differentiating CD with respect to CL. Let's do that. So when we do that, the first term produces CD 0 over CL squared with a minus sign, and then the second term just produces 1 over pi e aspect ratio. And then we need to set that to 0, so we're going to be trying to find the CL, which makes that 0. So we do that, and I'm going to call that CL star for the CL at the maximum lift to drag, or minimum drag to lift in this case. And it's easy to see then that the CL that does that is equal to square root of pi e aspect ratio times CD 0. Okay, so that's the first part of the problem. Now to just check that it's a minimum of CD over CL, we need to look at the second derivative of CD over CL. And if we take that second derivative, we'll find that it's equal to 2 CD0 over CL cubed. And then since all of these are positive numbers, CL at the maximum lift condition is a positive number. CD0 is going to be a positive number, so that means that this quantity is positive. So if that's positive, then CD over CL at CL star must be a minimum. Okay, so that just confirms that. Now we need to find CD star. Really what we need to find is the induced drag coefficient at this case. So CD star is the sum of the 0 lift drag and this term, which is the induced drag, right? So remember that this is the induced drag term, and I'm putting a star on it to say this is the induced drag at the CL star condition, which maximizes lift over drag. So now if I plug in CL star, I'll find that CDI star is equal to CD0. So we have the result then that at this optimal case where the lift to drag ratio is maximized, then the induced drag is equal to the drag at 0 lift. So that also then tells you that CD star is twice CD0 at this optimal case. Okay, which we're going to need now when we finally do the last bit, and that's find what the lift to drag maximum ratio is. And just plug in CL star over CD star. Okay, so CL star is the square root pi e aspect ratio CD0. CD star is 2 CD0. And I'm just going to rearrange that a tiny bit, just clean it up so that everything's under the square root. And so what I find here is the maximum lift to drag ratio is the square root of pi e aspect ratio over 4 CD0. And that's the story. So just a couple of quick notes about the results here. So what this tells you here is that if you want to maximize lift to drag, you're going to be looking for a high aspect ratio wing. Right? The higher that the aspect ratio is, the larger CL over CD max can be. And so that would be something we would expect. And in fact, you see that. Transport aircraft, sailplanes, other things where you're trying to get large L over D, the aspect ratios get larger for those types of airplanes. And of course, no surprise, we'd want to minimize CD0 to maximize L over D, and the span efficiency we'd want to be as large as possible also. So none of those are real surprises. One other thing to point out, I'm just going to go back to the previous page. This CL star result down here says that the CL at the maximum lift to drag is also dependent on aspect ratio and CD0 and E. I want to point out the aspect ratio part. So lift to drag, if we want to maximize, we want to increase aspect ratio. And what that means is that effectively you'll be having a larger CL. So the problem is going to become here that if I increase my aspect ratio, I'm going to need to be achieving a higher CL. And so at some point we're going to run into an issue here where the wing is going to stall if this CL gets too large. Right? We've seen this in the curves of CL versus alpha. That as CL gets larger, eventually it's going to stop getting larger and drop down. So while increasing aspect ratio looks like a good thing in terms of L over D, and it is generally, you do have some limits, and one of them is going to be that the maximum CL is getting to be too large, and you're not going to be able to achieve it. Of course, the other thing that's going to happen is a structural issue, which is for high aspect ratio wings, you're talking about long, skinny wings. The structure is going to be a difficult problem to actually sustain the loads that you have. So there's a structural problem with high aspect ratio as well.